Hmm?
You should monetize your YouTube channel.
Oh, why is that? Is there any value in it?
That's how you get money for your views.
I need to. Actually, there's been some discussion amongst myself and some other people of just doing that and retiring. I think you could probably do just as good a job, you could get just as good a paycheck doing that as you can what I'm getting, so, which is a sad statement, but okay. So I got the lights off there, and the projector's running, so let me see about, okay. Okay, so I'm trying to. Oop. So, oh, here we go. Let's see. Went to. Okay, so a quick, very, very quick review, kind of. Just because it's good to remember these kind of things, because there's a lot of this that's the base of this operation. And so what I'm going to do is just like go through it real quick so we can remember. So we had set up a, we had set up a B, and I know in the text we're not supposed to know this yet, but you've already experienced this somewhere. There's a lot that can be done with this, even to the point where we talked about how you want to project onto A onto B or B onto A, but there's a lot that happens here, especially when you start realizing that this is the case. And technically, I think we've been in 3D, but this is the first time here in a minute that we're going to use what you normally would do. That is, bring out a ruler and measure 2 meters, 4 meters, and 6 meters before we were doing angles. And angles, actually, I kind of view them as a byproduct or something you extract from the distances. We had this, and we found out just by going through this that A dot B is nothing more than AX times BX plus AY BY plus AZ BZ. And from that, we just multiply these, and we can figure out the length of A and B. And so we can figure out a lot of stuff just from this. And actually, if you think about it, if you want to go this way, I mean, it's up to you. But if you think about it, and you say, here's the I, if you have this as theta, you say this is like 10. You knew this was cosine of 10. You could treat this as though it's a dot product. In other words, the vector, this vector, A dotted with I, which I was going to write I, but I didn't, is equal to magnitude of A times the cosine of theta here. And so if you start thinking about that, you'll start realizing, okay, there's so much of my life that actually does revolve around this. If I start thinking this way, I don't have to remember some other things. So that's why this to me, is actually kind of beneficial for going on from here. Now, what he's about to do is he's about to say, okay, now we're going to go into this area where somebody uses a yardstick or a meter stick and measures things, and we have a rope attached between A and O, or O and A, and if I scroll down, he eventually should draw a vector. Okay, there's the same thing. Oh, then he draws the position vector there. Okay, that's wonderful. Let's do it like this. Let's just work off of this one. So here we go. Let's say you had a vector. Somebody was up here, tied a rope. Now, unfortunately, what happened to my straight edge? Somebody threw it away. Oh, no, here it is. See, that's a long straight edge there. So let's say here's your vector, O to A. That's not an O. So here, how about we do it this way, OA. So there's our vector. Or you might just say this. You might just say a vector going to A. And so if you look at this thing, you may say, well, okay, this is where there's a couple ways to do this. One is the concept of walking the axis and things like that. So that's what I'm going to do. If I'm going to walk the axis, I'm going to walk here into there and then down to here. So unfortunately, I got to walk the y-axis first. Then I can walk the x-axis. And then I got to walk the z. And so I'm walking backwards 6. So you're just walking the axis. Okay, so yeah, you could have walked x, then you could have walked y, and then you could have walked z. For that matter, you could have walked down, then across it. So it's essentially a box. You can walk one of the edges to get there. It's just, to me, whatever one they show me first, so I had to do that one, that's fine. So now let's add to it. What we're going to do now is I'm going to go over here and start MATLAB, and I'll show you a couple things. Now, I only have, he's only drawn one, so I'm going to draw another. And what I'm going to draw is I'm going to draw another one, say, I don't know, to right here. If that's 4, maybe that's 4 too. So I'm going to say this is B. So I have another vector that's drawn right here. So I'm going to draw a vector to B. So I'm going to walk the axis again. Well, first I can walk out here 4. And I don't have to walk this one. But I'm going to list it anyway just because, you know. And then I'll walk up. Now, there's nothing special. There might be something special about his, but there's nothing special about mine. So let's now look at the length of A. And what I'm going to do in the length of B, and I'm going to use the MATLAB thing for norm, and I'll put in A, but then I'll need to put in A first. I'll put in 4, and you know what? I'm going to use commas this time. And then I'll do the norm of A. And then we'll do that again with B. But give me a second and let me launch MATLAB, which it has been successful so far. And this is okay. So again, if you don't want to pay for MATLAB, you can go do the octave. Okay, it looks like you know what I'll do. Oh, but I can't do that. No, that's not, because all my lines are based on that. Sorry. So I'm going to have to lay this on top of here somehow. So first thing I'm going to do is enter A, and A was 4, 2, and minus 6. Now I'm going to do the norm of A. Oh, it's not? Okay, it's 7.4. So the norm of A, this vector is length of 7.4833. 3, 3, and probably a bunch of extra 3s. If I look at the norm of B, okay, so, you know, B would just be 4, 0, and 4. And, you know, the norm of it's going to be, you know, it's not going to be a, so B is equal to 4, 0, and 4. And then if I do the norm of B, it's going to be a non-integer number as well. A little shorter, 5.6569. Now, if I want a unit vector pointing in the A and a unit vector pointing in the B, all I have to do is do this. I did that backwards, sorry. A over magnitude of A. This time, it's not a happy number, so there's no integers that are going to come out of this. 4 divided by 7.48 is going to be a bunch of digits. And I'm going to do this. The B over that. And so let me do that on the computer real quick, and I'll show you something interesting. Let's see. So I'm going to call them U with the little a is equal to A divided by the norm of A. If I spell it right, the O becomes before the, anyway. Okay, so there's my norm of A. So as you can see, it doesn't end up being just these clear, concise numbers. They end up being, you know, there's nothing that's integer here. It's 0.5345, 0.26, and there's more digits. It just so happens that MATLAB generally likes to carry 4. You can do format long, and it'll carry a bunch more. I mean, I'll do that real quick just to show you. I think it's just format long if I type it right. And then the problem is it takes up, look how many digits, it takes up a lot of space. The thing is inside MATLAB, whether you do format long or format short, the numbers are inside there anyway. So it's just displaying to you more digits versus less digits. So if you don't mind, I'm going to go back to format short. And that way I'll just look at the 4 digits and just say, okay, that's fine. Now I'm going to find the unit vector in the B direction. B divided by norm of B. And there's that. So tell me, how would I find the angle between this vector and this one? Let me erase this other one. I'm going to erase this. So I want to find this angle. How would I find that? Okay, so I've erased the dot product, but I'll put it back. So if any two vectors, then essentially this equation sets. What would happen now if I said, okay, UA dotted with UB equals to the magnitude of UA, magnitude of UB, cosine of, well, this one points in B and this one points in A, so it's still the same angle, right? Tell me, what is this and that? They're both 1. So believe it or not, cosine AB, the angle is cosine inverse of UA dotted with UB. And that's all there is to it. So now, if you turn around and you're saying, okay, so I can do, there's a thing in MATLAB called a dot. So I'll do it all in one sequence. So I'm going to want to get angles in degrees. So arc cosine degree of the dot of UA dotted with UB. If I typed it right, got to have one more dot. It says 100 degrees. That makes somewhat sense. So it's about 100.89. I mean, I guess if I got a little, if this one came down a little bit more, I could get it to 90, but, you know. So, I mean, you start to see some of the things you can do. Now the other question is, let's say, and this, of course, maybe I shouldn't run ahead of myself. I'll stop there and then start going through the section. And then I'll go back to something else you can do with this, but I don't want to go there quite yet. So I guess I could, though. So maybe I'll do that. I'll go ahead and do that. So does this make sense first before I go do the next thing? It's just application of dot products. What would this mean? Okay, I'm trying to make sure I don't mess up. This vector points in the same direction as B. This vector is A, so it obviously points in the same direction as A. What would that mean? Let's just look at the left-hand side and see, what does that mean? What is the meaning of that? And we'll do it from this standpoint. Take any, man, if they're having a party, I don't know why I didn't get an invitation. So here's a unit vector. What did I call it? B. Just some old unit vector B. And here's some vector A. And so here's this concept of this projection.
Thank you very much.
Sunlight's out here, and it creates a shadow. And that shadow has to be, okay, the sunlight has to be perpendicular to this line, otherwise. And the sunlight's not that close. It's way out there somewhere off in infinity. So they had a party last hour too, and I didn't. I stopped. I looked over. They didn't have any drinks or food, so I don't need an invitation. So in fact, this is a projection. It's basically the component of this vector that's projected out onto that. That's all it is. So if you start looking at this, okay, what is it that I know that I can calculate? Well, okay, I'm sitting here in MATLAB. I have this vector, and I have that vector. That's all I need. I mean, I either need the left-hand side or the right-hand side. If we want to, I can show you that the left-hand side and the right-hand side are the same, but that's the link. That's what that means. That vector is what component of that vector is laying in that direction. The reason it's that way is because of this. Because that's unit 1. Okay, so now you see the length of that vector times the cosine of the angle between it. Well, okay, now it makes sense. Okay, that's the theta AB. It just so happens that, you know, here I'm in 3D, so I've got to turn around and figure stuff. Now I look at it as a plane, and it makes sense, you know. So if I want to, I mean, it's maybe kind of boring, but, you know, I can dot, what was it? A with UB. And let me see if I can, oh, here. Did I dot that right? Now, let's stare at, okay, now that's related not just to this, but it's related to that. Now, why would it, okay, so first of all, this is showing that the dotted projection of A onto B is a minus number. And at first you're like, oh, wait a minute, how come is that? So here I'll draw it this way. So I'm drawing the same drawing as I was over there. So here's the thing, here's my UB, but notice the angle. It's 100 degrees, right? So there's 100 degrees between these two. So it's like, ooh, it's back here. So, you know, the sunlight's still way off here, so the sun rays are coming. They're all coming and hitting the surface, which, by the way, I'll talk about that in a minute. I got a few extra minutes. Something interesting about that. So, lo and behold, one of the sunlight hits the end of this vector. It casts a shadow, and it's going like this. And so it turns out, okay, I forgot the length of A, but it's okay because I can look over here. I think the length of A was 7. So this vector was 7.48, because this was A, right? A. Okay, so it's about 7.4, but its vector, it was casting a shadow onto the ground that was that. Now, the reason it's negative is because this is the direction that's positive out that way. And so actually it's just that it's going the other way from the UB. And so it becomes a negative. And so you're thinking, well, the lengths are negative. What does that mean? There's inside out or whatever, you know. And so, so in fact, I mean, there's so much that happens with this that it really should be done first. So, you know, you go through, there's the sequence. You know, you got a vector, you can normalize it or find the unit vector in that direction. Then you can do all sorts of weird stuff with this. You can find the projection of B back onto A. So if you turn around, okay, I'm running in and out of space here, but you could do this, UA dotted with B. Curiosity, let's find out what that is, just out of curiosity. I mean, I don't think there's any standardization or anything that, okay, this time we're going to do U, A, and B, minus 1.698. That makes sense too, because still, the angle, they're still 100 degrees apart, and so it's gonna be minus, but a slightly different, you know, length. But the fact that they're 100 more than 90 means that, you know, it's going to come out to be negative. So now let's start scrolling forward, and maybe I can keep this part on here and maybe move MATLAB away and see where he goes from this position vector thing. But if I'm going to do that, but does this all make sense so far? I mean, it's just math, but again, there's a lot that you can do. Now, what's going to happen later is there's going to be cross products. And guess what? MATLAB has this thing cross. I can show you. I mean, it may not have much meaning yet, but here, let's cross, C-R-O-S-S, A and B. And there's a cross product. Notice it comes out as a vector. Now, notice this. Just a few tidbits or interesting things. And this is our right-handed coordinate system. Okay, so, I'm going to use my I, my J, and my K, right? So what I'm going to do is I'm going to come up with, just because we're here and I introduced this, let's just look at it. So a right-handed coordinate system, if I take I and cross with J, what do you think I get? Okay, so let's see if MATLAB will agree with us here. So I'm going to create a vector, call it A. So I'm ruining everything I had before in the sense that I'm going to take A as being I. Okay, so there's the vector A. Just a length 1 goes out the I, and then I take a B. So I'm running everything in the sense that I'm throwing away my previous A and B let me throw it away. Now I'm doing a different A and B. There is none of this is here anymore. And so I'm doing the cross product. So now I'm going to do B. Did I type it yet? No. So there's B. Well, B just runs along that one. Now I'm going to do this. Cross A. Did I just do a capitalized? No, yeah, there we go. So yeah, just, okay. The answer is it goes along the K. What happens if I flip it? If I say, I want the J crossed with the I. So actually, B becomes negative. So it says, hey, if you're going to take B, which is that one, you're going to sweep it to A, which is that one. It's going to point away from K. It's going to point down K, but the opposite direction. So that's the indication of a right-handed coordinate system. So, another, this is something you'll find out later. A cross B actually is the opposite of, when I say opposite, I mean the minus sign, the opposite direction. So it's basically that. Guess what? If you dot A and B, it equals to B dot A. It doesn't care. It could care less. So look at it. I mean, here's A. So if I flip the sign, flip the direction here, nobody cares. I just flip this with that. There's no flipping there. I mean, the angle's the angle. So it's just the same. So in fact, out of this cross product, you can say, okay, this is right-handed coordinate or left-handed coordinate or whatever, But all mathematics works off of a right-handed rule. So let's start flowing forward in this thing. So there, okay, that's why I stopped. It's like he gave me numbers that I could work with, and now he's not giving me numbers. He's saying, okay, there's a position vector. Okay, there's a box. Okay, before there's not a box. Oh yeah, by the way, there is a box, which means I could transition. I go from here to here to here, or I could go from here to here to here, or I can go. It just doesn't matter. I can get there either way. It's just I'm translating along the axis in a different sequence. X, then Y, then Z, or Z, then X, then Y. Oh, sorry, Z, then Y, then X. Doesn't matter, you get at the same spot. So, okay. Now he's saying, ooh, wait, I got two vectors, and I got a vector from one to the other. Well, okay, so I got RA and RB. Okay, so here's a weird thing, and I'm kind of hesitant to introduce it here, but I might as well. In dynamics, he has a different term for this one, and that is the vector that points to point B that originates from A. Now, this is a notation that you don't have to have yet, but this equation is kind of tiny, so let me write it bigger. RA plus R equals to RB. So in other words, if you go out here and you go to here, you get to the same place as if you went here. Like that's where the food is, and this is where you and I are. I go to A, and then I go out here. I was foolish because I took a longer amount of distance to get there. More than likely, I'm going to go straight to the food, so I'm going to go straight down B. So I'm not going to take this extra distance. So the distance I travel here is too far. But in dynamics, he has this notation that looks like this. And this is because what you're doing is perspectives. In other words, everyone, this is a psych class for a minute. So a psychology class would tell you everyone has their own coordinate system. We all observe the world from our own coordinate system. So from this coordinate system, the person that's sitting here, he sees that. So he or she is sitting here at A, looking there at B. This is the vector they see. This is the selfish coordinate system, the R, B to A. However, in dynamics, this is beneficial because it just so happens there's two types of motion. There's translation and rotation. And it turns out no matter where you're at, here or here or here, if you're on the same object and you're spinning, guess what? You all see the same spinning. So then, therefore, does that mean we all are seeing the same thing because we're on Earth? Well, that might have been the case until social media came in, and now we have all sorts of perspective. That's another psychological experiment. So, but in dynamics, they'll have that. For right now, we'll just say it's a vector. You know, you go to here, then out to here. The difference is the reason you want it this way, or have to do, someone may say, well, this is a bolt that's connected to the wall, and this is some sort of crane out here that's pulling this direction. But then this coordinate of location A might be at 5, 2, and 10, and the point B may be at 20, 5, and 15. So what's the vector of this rope? And so now all you're going to do is you're going to take, this minus that minus that, and that minus that, and that's going to be your vector. So what you're going to do is move this so that you find the R vector, which is B minus A. And I know that's kind of hard to read, but essentially, I can zoom it in a second, and that's all you're doing. Since the equation was RA plus R equals RB, you're only interested in R, you're basically going to say RB minus RA, or it's going to be if I take that minus that, I get 15I. I take that minus that, I get 3J. I take that minus that, plus 5K. That, if these are my 2 points, that is the vector between them. Now that I have that, I can work with that. Does this kind of make sense? So this is if somebody has 2 points and doesn't want the coordinate system to lay on one of those 2 points. That's all it is. Okay, then you can start working with it. So here's a cable, but now I can't go any further, so I guess I'm going to have to push the button. Hang on. Okay, so here's, I don't know that this is any better or worse than any other thing, but it doesn't matter. He's identified a hook here and one here. He also has this one and this one, but he just seems to be focused on this one. So you find the unit vector here. If the tension of all three of these is, say, well, actually there's a fourth one over there too. Say it's 1,000 pounds, and you want to know this one. What's the vector component? Find the unit vector, and how do you do it? Use the R drawn to location B originating from A. So in a dynamic sense, the vector that's drawn from A to B, from A to B, is just going to be this unit times, the length. I don't know I'll say the length of it. If you want to know the force, it's basically this unit vector, and say it's 1,000 pounds, just out of curiosity, just say we just say it's 1,000 pounds. Well, that unit vector is RB to A over RB to A, the same thing times 1,000 pounds. So we just found a unit vector that points towards B from A. And so this is what we're going to be trying to do. And then let's see, I'm going to jump by hitting that arrow. I think that's a bookmark. Yeah. But force vector directed along a line. What do? Nothing fancy, just like what I said. Whatever that 1,000 pounds is, that's a scalar. This is a vector, that's a scalar. This is a vector over the length now. So this is the difference in how the book does notation. So this would be 1,000 pounds times my unit vector which is equal to that 1,000 pounds, times the R vector over, over the length of that R vector. So this is actually what he's saying there. Of course, it makes sense here when you're squaring the square root. No, you're square rooting the sum of the squares. And then you have the vector sitting on top. That's the R. And so it's nothing really particularly fancy. So there's a nicely, looks like a rope to me, and some sort of hook on the wall. And guess what? The coordinate system's down here. Here's a boat. He has no coordinate system that I see. So you're going to have to come up with the coordinate system off of this one. And you're going to have to measure, you could probably stand out on the shore, measure the distance straight across to that, and then from where you are, maybe measure to here. That would give you your two coordinates you would need, and of course you'd have to figure out how tall, how high you're having to reach up to get to that level. In other words, let me say it like this. So in other words, if you were at the shoreline, you were actually trying to figure this out. First thing I see is that you could parallel, so this line parallels the line of the shore. Then what you'd have to do is figure out how far it is perpendicular. So what I would do is come over, then I would go perpendicular right here up to say whatever it is. So somebody's going to have to stand there with a bunch of yardsticks taped together or something, or I don't know. And then they're going to have to go across to here. Now, it doesn't look like it's 90, but that would be 90. So you'd have to figure out this, that, and that. That would give you the distance or the vector. You could figure out what U was at. You don't have to do that in these problems because he's going to draw a coordinate system on there for you. But if you were standing on the shoreline and you were actually tasked with the thing of doing that, that's what you could do. Here's what I mean. Let's scroll down. He's got to have an example. Okay, so here's a video with an example, but there's a video, so you can go ahead and do that. I'll let you look at that one. I'll find one that's, okay, here's a dude pulling, okay, okay, oh, what if I click that? Okay, the picture comes up, but it stays in the center. Okay, I don't really know how to make it any better than that. So let's just draw a vector. So what I'll do, he's given me a coordinate system X and a Y and a Z. So if I were to draw the vector A, you don't go out X, you don't go out Y, but you go out 30. Okay, then I'm going to draw a vector to B. Okay, so I got to translate myself to get out there. How you want to do it's up to you. You could go, I'm going to try to go the X, then the Y. I'm going to go X, then the Y, then the Z. So if I went to B, running out the X, I would go 12 out the X, minus, what is that, 8? Minus 8 out there, sorry. And then you got to go up 6. Okay, that little thing is confusing. I think that's where the mouse is sitting. And there you go. So sorry, I wrote the B there, but then I wrote it there as well. So now, if you want to draw, now to me, probably what's going to be asked is the guy's pulling the rope. So I'm going to find the vector this way. So if I do that, then I say RB, I meant to say RA, sorry. RA plus my R is equal to my RB, or my R, RB minus RA. So actually, technically, let me do this. This should be RB. This should be RA. And so I'll subtract those two after I take this quick energy drink here. Your energy drinks have caffeine. Mine has no caffeine. Mine actually has, I should have one with more calories. Mostly because if I were in your shoes listening to me, I would fall asleep. So my energy drink would have to wake me up. But I'm up here and I don't think I can fall asleep and do what I'm doing. So I got to have energy to keep moving. So if I do that, what was I doing again? Oh, I was taking this minus that. Okay, RB minus RA. Maybe I am falling asleep. 12 minus nothing. 8 minus nothing. Now, make sure I'm doing this right. I'm going B, so I'm going B minus 30. Isn't that minus 24? Now, the other way you can check this is let's see if I'm doing that, okay? This is a different way of doing it. Okay, I'm going to go down to this vector, and then I'm going to go to here, and then we go to here. So if I just wanted to do that vector, R, what I'm doing first is I'm running backwards. I'm running in the opposite direction. I'm going to write this all sort of weird. 24K. So my path is I go to here, then I go minus 8J, and then I go plus 12I. Now I've done it backwards, but if I rearrange it so that my I comes first, then my J, and then my K, did I get the same thing here that I got over there? And I think I did. Sometimes you can just run the coordinates from point A, boom, zoom, zoom, and you basically that's your vector. Okay, now that I've got that, I want to find the unit vector that direction. That's just going to be R over magnitude of R. And now I'm just going to rely on MATLAB, if y'all are okay with that. Okay, so if I do that, okay, so I'm going to do a clear and a clear of the screen. So my R was equal to 12 minus 8, 4. The reason I'm doing commas instead of the semicolons is because if I do semicolons, it takes up more vertical space. So this, it takes up one line, and I can see more, and things won't run off the screen as quick. Does that make sense? So a unit vector would equal to R divided by the norm of R. Did I just type? I did that again. Norm of R. Okay, so now let's say it's 1,000 pounds. So if I want to know that guy's probably not pulling 1,000 pounds. Okay, so maybe he's pulling 50 pounds. Does that make sense? So he's pulling the rope with 50 pounds. So if I want to know the force, it's equal to 50 pounds times U. And that's his force. That's the force that spot up there at A feels. And it makes sense. So it feels like it's pulling 21 pounds in this direction, 14 pounds in the minus Y direction, 14 pounds this way, and 42 pounds in the minus Z. And that's what this little bolt or connector at A feels. Now, if I want to, and I don't know that this might be pretty close to scale. So I add that 14, and then I add the 21, and guess what? I end up pretty close to being on the rope. And actually, the point should be on the rope. Unless your scale was so big that you went all the way down here, but okay. Oh, I'm getting tired, and it's So let's call it quits. But let me just scroll forward and see what else he does. Okay. Okay, so he found, okay, he said 70 pounds. I should have made 70. I should have looked down. 12, 8, and 24. He found the thing. And actually, look, it clipped it. Oh, you know what? No. It's hidden behind the, it's hidden behind the picture. So it's 28 something. And then 70 pounds. Okay. The fact that he picked it as 70 meant that things became integers again. Man, I'm tired. I may have to go to the car and get a Pop-Tart or something. Oh, so what now? So, symbol? Which symbol? Okay, see.
I had got the answer from this. I'm trying to figure out that one.
Okay, express your answers separately. Using a parallelogram, add these vectors geometrically to determine the displacement of the boy relative to the tree. That's a good question. So
I'm trying to find the vector for this one, one. Find the components of the vector, but I'm getting confused on what the x component would be for this one.
Okay, I guess I'd probably have to read it more. Here, I tell you what, let me draw it. Which one is that? 12? Okay, wait. Okay, so let me see. I might be able to draw that one up on the screen.
It's from the 10th one.
Okay, so let's do this. I'll go to, so it's not dynamics, it's statics. Okay. 10th one, and then assignments, and then it should show up in a list, and then there we go. It's the 10th one? No, wait.
It's the 10th one. It's showing up.
Really? Wait, is it show up like that? No, that, is it? Oh, it is. Oh, okay. Okay, so brother and sister are playing in the woods, and suddenly they're separated. The last place he remembers seeing his sisters is at a particularly large tree. The brother traveled D1 at that, and from the tree, and turned and traveled to D2. Okay. Meanwhile, okay. The angles are given with respect to it. Determine, okay, so now that we got that, so we slide down, what's the question? Okay, there's the tree. Oh, good. The tree. He went to here, and there's the boy. Okay. Position of the boy. Okay, so, oh, okay, does he want to know the distance?
Yeah,
So what?
About the distance for the in meters, I think.
Oh, okay. Okay, so I think I see, what is he doing? He's saying D is the distance, then he puts a comma, and then he puts 50, and then M, comma, degree. That's a weird way of doing the answer, but it's probably just being restricted by the computer system. Let's see if I can make it. Okay, so let's see if we can hammer this out. Yeah, this is, I know.
I'm trying not to because I know it's pretty simple, but like I said, our brain don't.
Yeah, I get it. So let's see. He's got, okay, so D1. Okay, so D1 is 24 and 25. So this is 24 and 25. Then he says D2 is 11 and 135. So this is where we're working at right now. So he wants to know the D to there, right? So no, D. Yeah. So I guess there's two ways you could do it. One would be the position to, I guess I could say that's location 1, and this is location 2, maybe? So if I did position 1, the 24 cosine 25i plus 24 sine 25j.
So it's like a projection.
Yeah. So in me, I just think of that. I think, well, I can project it onto there, and then that distance from here to here will be the sine. This will be the cosine. That'll be the sine. That'll get me to there. And then r to 2. Now, that's the thing. This is not the r directly to 2. This is the r directly to 2. Does that make sense?
Yes.
2 if you were on 1. That's where I kind of like that symbolism. Yeah. So if I do that, it's 11, and it's still projected this way, even though it's going to project over there. Cosine 135 I plus 11 sine, which I wrote wrong, sine 135 j.
So basically, they're still saying that it's on the x-axis but projected.
Yeah. So this will be a little bit negative. Don't know how much, but it'll be a little bit. So then, this is why I like this notation. If I wanted to, R1 plus R2 relative to 1. So what you'll find out in dynamics is the subscripts, if you wrote them, then the subscripts come out to a 2. And that's the reason they write them that way. And it's so convenient because sometimes you don't even have to think. And it's good to make mnemonics like that so you don't have to think. So actually, if you're just looking for the distance would be 24 cosine of 25, it's 25, plus 11 cosine 135. That would be the x distance because you're adding that, and then square plus, yeah, that's 11 sine 135, which that'll end up being positive, and then that'll be the distance. Now, the other thing was the angle. He wanted to know, I guess he wanted to know this. So that one, you'll have to do a couple of things. One, if you had this, and you wanted to know some angle, and you had the x value and the y value, let's see, the tangent of the angle is equal to sine of the angle over the cosine of the angle. And so if you look, I mean, I know that you probably see past what I'm doing, but I got to do it over hypotenuse. Cosine is the x over the hypotenuse. The sine is the y over the hypotenuse, so you get y over x. So then if you want to know the angle, take the inverse of the y over the x. And so the y will be just these two added together will be your y, and these two added together will be your x, and that's it. So then you just take that number divided by that, and then take the not the untangent, the arctangent, inverse tangent, arctangent, whatever you want. Some books list it like that. In MATLAB, you can't do that, so MATLAB has that. And then you want degrees, you have to put a D at the end of it.
Can I take a picture of it?
Sure. I left the stream going too, so it's on the stream. I try to leave it going as long as, I hope I left it going. Uh-oh, I better check. I try to do that. Wait a minute. Uh-oh. Is it still going? Yeah, it's still going. Oh, okay. I like to do that because, that way, other people can have, where did it go? There it is.
This is probably some
So the angles are given with respect to east.
That's what I was confused about. I was like,
Oh my gosh. So they're saying north, and if you go east, and you go south, and you go west, counterclockwise. Clockwise runs that way, so. Okay.
it kind of confused me a little bit. I'm like, okay,
I
I don't think they have to clarify.
Yeah, I haven't seen it. I guess I should be used to seeing that, but haven't seen it quite expressed that way before, but that's okay.
Because at first I was just looking at it as like regular calculus stuff, as like AX,
Yeah.
AY. That's why I was kind of confused on it a little bit. So just to go back over it, this would be 24, because this is the distance.
Right.
Cosine.
Right.
With respect to X.
Yeah.
And then the angle.
Right.
And then for Y, it'll be the same thing. but
24
just with
sine,
Okay.
and then 11 cosine, and that's where I stopped, and I had to pause for a minute, because that is as if somebody put a coordinate here, and then then we're working off that. That's why I do like that notation better, because then you realize you just move your coordinate to where you are, and you work yourself off of that. But I wish the same person wrote the dynamics, the statics. I wish he would have spent a few minutes at statics doing that, because then when you see it in dynamics, it's nothing new. So
I'm gonna take a picture of it real quick.
Oh, okay. Shoot, I got rid of part of it there. Okay, I think that was tangent of theta. I think that was arctangent, and this was theta. And that, that was, I was just writing, yeah. That was related to what MATLAB likes to see. Oh, okay. All right, good deal. I'm going to take a nap now. I really should. I'm tired, but I got to do another class now, so.